Okay, test one more time. Okay, good. I think you all can hear. So today lecture I will cover about the tree balancings problem. I hope I can finish this part. Then yeah, then next week probably Monday I will cover a little bit and wrap up my first part. And Friday probably can be a Q&A section for you to ask some question. Okay, then the lab test will be during the recess week on the Thursday. Should be when 3rd March, is it? Yes, 3rd March. Yeah. So the detail will be released by next week. We'll let you know the venue, the location, and the time slot. So we'll be split you into maybe 2 group or 3 group, 2 to 3 section. Yeah. I will cover it on Monday, I think. Yeah. That is just an application only. That one will be just an application. So today will be the tree balancing. That is, yeah, I think this thing we have covered. So before I talk about the tree balance, lab test will be 4 questions. 4 questions, so 2 hours, 4 questions. Each question will be on average should be about half an hour question. Yeah. So definitely will not be that difficult as your assignment. Should be something similar or yeah, like the lab section question. So again, a lot of people keep asking me about the lab section. Is it compulsory? The objective, I don't want to make it graded. Yeah, if you manage to do it by your own, it's fine. If you not manage to do it by your own, it's good that to attend it and learn. And also familiar the lab environment interface, because during the lab test we will use the school computer. Make sure you know how to use the code block or this. Okay, if you don't know how to use a code block, that is your choice. You want to directly code it, is fine. But during the test, only code block is available. Yeah. So one question on linked list. It may not be in that format. Yeah, I would say that to me, I look at it is all the data structure is just all are the linked list. So if a stack or queue is still a linked list, tree is also another kind of using the linked list to construct the tree. And the concept about the stack and queue is a concept. One is the last in first out, the other one is first in first out. Tree is just a non-linear structure, but in the end we construct it is still using the linked list to build out this data structure. In fact, those data structure also can be done by an array, but just like there's an advantage having the linked list sometime. Yeah, depend on the question application you have. Yeah. So okay. Yeah, you can attend multiple times. It's just like you are using the same platform. So again, you should familiar the platform now. So that will be the style will be very similar to the platform, but just instead of give you a few hundred hour to try, now the test only have 2 hours. Yeah, it's not an open book. So also there's a hidden test case. You only know the correctness, but you wouldn't know what is the test cases exactly. Yeah. That means the test case is not visible, but you know whether you pass or fail on that particular test case, or whether there's a runtime error or not. Yeah, the platform will feedback to you when you attempt it. Okay, so quickly go through this lecture today. So last lecture I have mentioned that in my definition, the height of a tree is the number of edge. Okay, then the depth and the level of a nodes I also use the number of edge and from the nodes to the root. So one is from the root to the leaf, then the other one is from the nodes to the root. So you expect that it's opposite, the height of a tree and the depth of a nodes. Then when we set the empty binary tree, that means there's no nodes. In that case, that particular tree, the height of the empty binary tree, I define it as -1. Yeah, there's no right or wrong. There's actually nothing inside. Of course, there's no edge. But one node's also 0 edge. So in that case, to distinguish one node's tree and empty binary tree, I will define it as -1. The height of an empty binary tree is -1. Then we have show the full binary tree. Full binary tree is what you see here. In this one is the full binary tree. The height with no missing nodes. A binary tree of height h with no missing nodes. That means yeah, all the internal nodes have 2 children, and the leaf is only at the bottom. Then complete one is a complete binary tree. Is the binary tree is considered a full binary tree up to h-1. That means the bottom, this part, yeah, is not fully filtered. So it's only filtered partially. So it's considered complete binary tree. And last lecture have shown you that if you have a complete binary tree, then your binary search, if you have a complete binary search tree, in that case, your binary search, the time complexity of the binary search will be log n, will be big theta log n. So that is what we hope we can get such a tree. But in practice, a lot of time you find that it's very difficult. So today lecture, I will show you to construct a binary tree I will show you today that to construct, always trying to build a complete binary search tree is very difficult or very expensive. So instead of having a very bad binary tree, or you get a very good complete binary tree, we're trying to find something in between, which is the balanced binary tree. It's a binary tree you can see on top corner. And which the left, any nodes in this binary tree, the left subtree and the right subtree, the height of the left subtree and the height of the right subtree have the difference by at most 1. You can pick any nodes, for example 23 in this example. The left side, the height is 1. The right side, the height is 1, 2, 2h is 2. So this is 1, this is 2. So the difference, the height, the left subtree and right subtree, the height of the left subtree is 1, the height of the right subtree is 2, so 2 minus 1, which is 1. So the difference is 1 only. So any nodes, the difference only at most 1. Can be 0, that means left side and right side are perfect, are balanced, are well balanced, have the same height. But some location you may see that the left side may be a little bit higher, or the right side is a little bit higher than the left side. So that is considered a balanced binary tree. Yeah, why? You can see that you have, last lecture have shown you, if you have a, this one also not a, this one can consider a complete binary tree. If you have a complete binary tree, the search time, the time complexity of binary search will be in log n. But if you construct a tree into this is a linked list, then the time complexity of the search is big theta n. This one will be the average. I'm talking about the average will be log n. Yeah. So you'll find that if you have a tree, if you have a binary search tree, this is your search time will be log n. But if you're trying to insert, for example, I'm trying to insert, construct a 396321. Yeah, this field number. I construct a tree. First I insert 9. Then after that I insert 6. If I didn't do anything, like what you learned in the earlier lecture to insert the nodes to construct a binary tree. So because all these number always smaller than the earlier one. So 9632. So you will insert the nodes always at the left, as its left subtree. So eventually this will form a linked list. Then when you do the search on this particular tree, it will be exactly same as having a singly linked list to do the search. So the time complexity will be big theta n. And even you have this particular tree, you will find that every time you insert a node to a balance or a binary tree, a complete binary tree, you will soon become a unbalanced tree and no longer become a complete binary tree. So in this case, you will find that every time you insert a node or you remove a node, you need to rebalance it. Otherwise, the tree very soon will become very inefficient for the search. So we need to do the tree balancing every time we insert or remove a node. So this is one of the approach we are going to introduce you is a AVL tree. So what is the balance tree? So a binary search tree is height balance, or we said it's height balance, or you said it's balance if the difference in the height of both left subtree and right subtree of any nodes in the tree is either 0 or 1. So-called the most balanced binary search tree is each tree nodes has exactly two child nodes, except the one at the bottom, 2 level. So that's mean on top. Yeah, this is the one. On top, you have 2 children. Only this part, some of them only have 1 child. Some of them have no child. So this is a most balanced binary search tree. How about these 2? Is it okay to have these 2? Is it these 2 is the balanced binary search tree? How about this one? Is it balanced? This one, the first one. Yes. This one, yes, man. Here you have the left side, the height is 1. The right side, nothing. It's an empty tree. Empty tree, just now I mentioned, is -1. If it's -1, here is 1. The difference is 2. So this is the unbalanced binary search tree. And this one, this one I have mentioned is the balanced binary search tree. Yeah, this one is the I think I missed out this. This one, these 3 are not. Just like I think this one is the most balanced. This one is not the most balanced, because if you took ignore the bottom 2, you can find that 14, 73, 94. They are only balanced. These are only the balanced binary search tree. Just like I said wrongly. It's not the most balanced. It's a balanced binary search tree. Yeah, because 14, 73, 94 only have one child. So that case, they didn't fulfill this. The middle one is the most balanced one. It's the most balanced one because you took ignore the bottom 2 level. This is a complete a complete binary tree, which is a complete binary tree. So this is the most balanced binary search tree. Yeah, this is the most balanced binary search tree. Because ignore the bottom two level, yeah, this is a complete binary tree. If this is the case, then you will consider it as a most balanced one. The bottom, you can see that 14, 73, 94. They only have one child. For this case, 14 and 93, yeah, they have two children. Except bottom two level. Yeah, so you just ignore these two level. You'll find that each node 70 got two children, 14 got two children, 93 have two children. So this is the most balanced binary search tree. This case is not, because 70 yes, 23, 93 yes. Ignore the bottom two level. So 14 is not, only one child. 73 only one child. Then 94 only one child. In this case, yeah, this is not the most balanced binary search tree, but it is the balanced one, because you pick any nodes in this subtree, any nodes. This one, yeah, left subtree, right subtree, same height. 23, left subtree, the height is 1. Right subtree, the height is 2. So 2 minus 1, yeah, is still 1. So 23, the difference is 1. The subtree, 2 subtree, the left subtree and right subtree, the difference is by 1. So they are at most 1. Either 0, the difference is either 0 or 1. Yes. So any nodes, you pick any nodes, must be any nodes. That means all the nodes you need to check. Every nodes you need to check to make sure that any nodes, they fulfill this criteria. Once they fulfill this criteria, I would say that it is a balanced binary search tree. The left subtree and right subtree, the different, yeah, the difference in height of the both subtree, left subtree and right subtree, at most 1. Okay. So one case 31 got one child, isn't it? 31 got 1. If you're talking about this one, okay, 31 have 2. Oh, this one, okay, bottom 2 level. So you don't care this part. You only look at this portion. This part you don't need to care. You only look at 70, 14, and 93. 70, 2 children. 14, 2 children. 93, 2 children. So this is the most balanced binary search tree. The first case is unbalanced one. This one is unbalanced one. Because 31, as long as I find one case, one node didn't fulfill this criteria, because it said any nodes. So as long as I can find one node, yeah, it doesn't fulfill this criteria, that means this is not a balanced binary search tree. If it is not a balanced binary search tree, I don't need to check whether it is a most balanced or not. Definitely it's not a balanced one. Okay, so that is the definition. So what I need to do next is trying to get this binary, yeah, to build out my 3-0 way have a balanced binary search tree. At least, although it's not a complete binary tree, but this, you can see that by doing any search on this particular binary search tree, your search time will not be too bad. Should be almost also still the log n, because most of your nodes still at the bottom. Yeah, then you need to search. Yeah, your height is well balanced. You don't have something like a linked list structure in the tree. So the search time should be in log n. How come the height greater than 1? The height greater than 1? No, the difference. The height greater than. First case, I still don't get it. How come height greater than 1? No, the difference. I'm talking about the difference. If you look at 31, this side, the height is 1. The left side, the height is 1. The left subtree, the height is 1. The right subtree, nothing. So the height is -1. So left side is 1, right side is -1. So the difference between the subtree is 2. 1 -1. 1 minus -1, 2. No, the right subtree is -1. Just now I already mentioned. I define that when you have 1 node, the height is 0. When you have no nodes, then the height is -1. Yeah, that is the definition. Of course, you find some book, some online resource, they may define it differently. They may define 1 node is the height is 1. Then no nodes is 0. There are some other people use this definition. Well, in the end, on this case, is still the same. The balance, the difference still the same. So it doesn't matter you use the number of edge or you use the number of nodes. Because the key is not the height, the key is the balance, is the balance factor, which I'm going to mention. So there are 2 ways to balance a tree. One most intuitive way is resort out the tree structure. Another way is, which I'm going to talk about it today, is the AVL tree. Is because you'll find later I will show you that the first one, yes, you will give the best, most balanced binary search tree, but the cost is not cheap. The AVL tree, they only do it locally. They balance the tree locally, and in the end, you only can ensure that any nodes in this tree, the left subtree and right subtree, different by at most 1. That means it's a balanced tree. But you cannot guarantee the whole tree are a perfect, a nice, complete binary tree. It's just balance only. You only balance a tree. So, but the cost, the time complexity is much lower than the first one. So this one actually is invented by 2 Russians, in 1962. So it's quite long time ago. Okay, so the first one, actually quite straightway. You have a, just I have mentioned, this is the unbalanced one. Because of this 31, you can see that it's an unbalanced tree. You want to get the balanced tree, you want to do the balancing. One way is sort out the data. So what can you do? You use the, first you can try to sort it out by using the in-order traversal. I think my animation not correct. I can use the, I'm supposed to use the in-order traversal. I use the in-order traversal. I will visit this node, travel to the left, travel to the left, travel to the left. Then you visit this nodes. Then you am I right to set this? I think I typed wrongly. Should be pre-order. In order, correct. In order. I travel to the left nodes. In order traversal, I always travel to the left subtree. So I travel to the left subtree until the end. I visit this one. So 7. Then after that, I return here in order. So I will process this one. This is a second node, 14. Then after that, I visit this node, the right subtree. This is the third one. Then fourth one. Fifth one. Then the right side for trying to travel to the left. So 71 will be the next one. 7, 8. So that means if you have a binary search tree, whether it's balanced or unbalanced, once you use the in-order traversal, you are sort out the you can sort out the data in this case is in the ascending order. 7, 14, 23, 31, 70, 71, 73, 93, 94, 99. Okay, so after that, you were just trying to pick the middle one to insert the tree, to build the tree. So this will be the first node you build. And then after that, the left subtree will be this 7. Yeah, then again you will pick the middle one, 14. You'll build the second nodes at the left side. Then 7 will be the left nodes of 14. Then 23 and 31 you will insert at the right. So then similar to the right side, you will repeat this procedure to pick the middle one, insert it into the tree, then insert in the middle, insert its middle, then last one will be this. So you will construct this a balanced tree. Yeah, every time you take the middle element of, after you got this, you put it into an array. You store it into an array. Every time you pick the middle one, can quite easy to get it because you store into an array. You know the array size, you know the index, you can easily find the middle element from the array. So every time you take the middle one and then insert into the tree, slowly, eventually, all the nodes you reinsert, you will become the most balanced binary search tree. Yeah, you pick the top 2 level. Yeah, all are 2. Okay. But you notice that by doing this, the time complexity is not cheap. Yeah, this is the way. Every time you just trying to do the in order traversal, and then you do the insert the nodes, you take the middle one, you give me this array. After you do the in order traversal, you got the array. Then every time you just insert the nodes. Yeah, take the middle element, insert into the nodes. Then travel to the left, insert. Yeah, but you find that in order traversal, this step, the cost is already in. Is in linear. Then you insert the nodes again. This procedure is another one, also is in linear. Depend the number of nodes. You have how many nodes, you have to run this particular algorithm to insert those nodes into the tree again. So the time complexity, yeah, the first step linear, the second step still linear. Overall, of course, is still a linear. So the time complexity. Moreover, you need additional array. So that will be last less than. Yeah, last should be greater. Last should be greater. Okay, sorry, typo. Yeah, last should be greater. Maybe later I will correct it. Discuss. Hopefully I correct it. Later I'll update it. Should be greater. Yes, thanks. Yeah. Last must be always greater than the first. Yeah, then you will run this potion. Yes. So you insert. So you'll find that the cost is not cheap. So yeah, people start thinking, yeah, that 2 Russian trying in 1962, they start thinking can I find a way to use, well, I want to get a balance. I just need to balance. I don't really need that good tree. I just need to balance the tree. As long as I wouldn't always only have a left child, or I only have the right child all the times. I trying to have each nodes always have 2. Try to have more 2 children. Maximum you only have 2 children. As long as every nodes have 2 children, as many as possible, then the whole tree will be well balanced. Yeah, then it's good enough for me to do the search in log n times. Close to log n times. Yeah, so they find that every time you insert, you will find that every time you insert or remove a node, your tree will be, even initially is a balanced binary search tree. After you remove or insert a node, you will become unbalanced. then we need to balance it. And then they're trying not to reconstruct the whole tree. So they're trying to just locally balance it to let it, yeah, because once you insert the nodes, you only affect those nodes along the path become unbalanced. So they just need to balance it along the path you insert the nodes or remove the nodes. So yeah, and as long as they just want to make sure that in the end the balanced tree, the left subtree of any nodes or every nodes different by at most one. Yeah, they just want to fulfill this criteria to get a balanced binary search tree. So they're not going to build the most balanced one. They just want to build a balanced binary search tree. Yes, it's a constant time, but you need to do it n times. To access the middle element by array, of course, is a constant time. Because you can, yeah, the good thing for array is that you can randomly access. So that particular step is in constant time. But in just now that case, you need to do it n times. Because every node you need to insert into the tree. So you need to do it n times. So in the end, the overall is still big theta n. So for the earlier that example, that case, this one, you definitely need to run in linear times because you got n nodes. And I use an array so that when I access the nodes, I only take the constant time to access it. I can directly get it. Yeah, this is the constant time. This one is each time, each iteration, you just need to run constant time. This one also constant time can finish. Yeah. Oh no. Yeah, insert nodes. You just insert a nodes. This one may not be. This one, I think more than that. Actually, I think this one more than that. Actually, yeah, if you consider you insert a nodes, starting is one nodes. Then when you have two nodes, you need to travel 2 times. Then you have 3 nodes, you need to travel 3 times. Yeah, so I mean first time you insert the nodes is 1. Second time you insert the nodes is 2. Third time you insert the nodes is 3. Fourth time you insert the nodes is 4. You need to do the comparison and travel. Yeah. It may be left, may be right. You may be insert to the left, maybe insert to the right. So am I right to set that is you insert a node to the left, to the right. But first time is 1. Second time is you need to insert into two into. First time you insert this. Second time you insert it to here. Third time you insert it, probably will be here. I think it's still linear. It's still linear because you may take log. You insert, you try, because it's a balance. So every time you insert, it's either left or left, right, left, right, left, right, left, right. So overall, you will insert, this one will do one comparison. You have 2 nodes, you will do this one 0 compare, this one insert 1 node. You need to do comparison 2 nodes. Overall, I think it's still linear. Yeah, overall, I think it's still linear because you insert n nodes, and they are the worst is you insert to n times. That means you got n nodes over 2. The first node is 1. If it's a linked list, you insert the nodes. First one you insert, you do one comparison. The worst case is you insert to form a linked list. First time you insert a nodes, you get 1 node. Second times you insert it, you need to do 2. You got 1 node. first time is 0, more precisely. First time you don't need to do any comparison. Second time you do one comparison. Then third time you insert, you got 2 nodes inside, you need to do 2 comparison, and so on and so forth. In the worst case scenario, you need to do so many comparison. Then the construction is 0. You got n nodes. You got n, you do it n times. The first one is 0. The second one is n minus 1. In the worst case scenario, the insert node is in n square. Is in n square. This particular one, the worst case will be in n square. That's when you insert all along is form a linked list. But in this case, it will not be that worse, because you already ensure that you every time you will insert from the middle. So you will definitely will insert this one, will do 0 comparison. Then this one you will do 1 comparison. This one you will do 1 comparison. This one you will do 2 comparison. Then this one you will do 2 comparison. This one will do 2 comparison. This one will do 2 comparison. In that case, that means you got 1 case is 0. You got 2 case is 1 comparison. You got 4 case 2 power to 2, which is 2 power to 2, which is there are 4. There are two compare. Sorry, there are 2 comparison, but there are 4 nodes need to do 2 comparison. There are 8 nodes need to do 3 comparison, and so on and so forth. So in the end, it should be depend you have how many nodes. Yeah, maybe this one I will add it later. Yeah, this one need to do probably. I think it's should be still linear. Overall, it's still linear. I will show the proof later. Yeah. So anyway, for sure this one you will be more than linear times. And then this one we don't want to do that bad. We want to improve it. Okay. So how to improve the the last mean? The first, because every time you divide by half. So the first and the last is the index of the array. Yeah, the first will be here. The last will be here. After you insert 70, the first will be here. The last will be here. Yeah, so it's first, middle, minus 1. The last will be here. The first will be here. Then you repeat the nodes insertion. Okay? Yeah, this one later I show you the proof. I fixed the AVL3 first. So this AVL3, you will find that you need to locally balance it. After you insert a new node, like this 28, you will find that after you insert the 28, the tree is unbalanced. This one not yet. This one still balanced. I need to insert another. No. After I insert, let's say I'm trying to insert another one at 1, 2, 1. Then this one I need to insert 29. Let's say if I want to insert 29 into this tree, you will find that 29 smaller than 70. So move to the left. 29 greater, then smaller, greater, then greater. So 29 supposed to insert here. But after you insert 29, you will find that the tree become unbalanced at here. At here. This one is unbalanced. 31 also unbalanced. After you insert, you will find that you have this problem. Then 1, 2, 3, 4, 1, 2, 3, 1. So this one also unbalanced. These nodes also unbalanced. So because of this one, 70 also unbalanced. So these 4 nodes will become unbalanced. So I need to find a way to rebalance the nodes such that these 4 nodes will become balanced. The rest still remain. So one thing you can observe that when you insert a new node into the tree, you only affect the nodes along this path. Right? When I insert a new node into a balanced tree, then the tree become unbalanced. But why it become unbalanced? Because along the insert path, these 4 nodes become unbalanced. So I need to find a way to balance them. The rest you find that you won't affect. Yeah, 93 still balanced, 73 still balanced, 94 still balanced. Only these 4 nodes is unbalanced. So how to do it? So first we need to define something called balance factor. Balance factor, that means I just need to calculate the height of the left subtree and the height of the right subtree. So let's set all the leaf have a balance factor which is 0. Left side is nothing, right side is nothing. So the difference is 0. Then after that you can find that 31. Left side the height again not simply take the balance factor. The height of this one is 0. The height of this one is 0. So 0 minus 0, you get 0. So the balance factor of node 31 is 0. Then how about this one? The 7, node 7, the left side is, the height of the left subtree is -1. The height of the right subtree is 0. So the balance factor is -1 at node 7. 9 also, 99, nodes 99, the left side, the height is 0, right side is -1. So 0 minus -1. So the balance factor at nodes 99 is 1. 14 is this side, the height, the left subtree, the height is 1. The right subtree, the height also 1. So 1 minus 1. So nodes 14, the balance factor is 0. Okay, take notes. This is 0. Not just simply take the balance factor minus. You need to calculate the left subtree height and right subtree height, then subtract it. Similarly, for 93 is -1, 70 is 0. So I need to know the balance factor of each node first, so that I can find which one is not 0, 1 or -1. So in this case, these are the balance subtree, balance binary search tree. So all the nodes are either 0. The balance factor is either 0 or -1 or 1. So this is fine. No, this the whole tree is the AVL tree. So this one of course is also a AVL tree. No problem. This one still a AVL tree because all are balanced. I haven't insert any nodes yet. So assume you have a balanced tree, which is So this one also a AVL tree. Also can known as a AVL tree. Fulfill all these criteria. But once I insert a node, then the story will be different. So let's say you have this. So I need to have some small function to help me. So therefore I introduce the height in each node. I need to know the height of each node, because every time I calculate, I need to the balance factor. I need to know the left subtree and right subtree. I think there's another typo here. Yeah, should be. Every time I will go to call the get height. Okay. Okay. Yeah, get height. I need to know the left subtree height and right subtree height. Then I need to do the subtract. and then find out the balance factor of each node. How come 14? Yeah, the left subtree. So what is the balance factor? The left subtree is the height is 1. The right subtree, the height is 1. So the balance factor at 14 is 0. This is 1, this is 1. Of course, it's 0. Again, don't use this number minus this number. It's height minus the height. The left subtree height and minus the right subtree height. If it's, yeah, okay, again, correct. This one should be -1. Get the height. If it's a null pointer, if you yourself is a null pointer, your height is, yes, you are right, should be negative. Yeah. Why I didn't change it? Okay. Yeah, should be this way. So the balance factor, if you are the null pointer, that means you are balanced, you are well balanced, so you are 0. Okay. So once you have this thing, the next step, you will find that if you want to insert a node, there are a few cases. There are three cases. The first 2 cases, no problem. The problem is at the case 3, which is make your tree become unbalanced. Let's see the first case. Let's use the example to demonstrate. So if I want to insert 25 into this tree, into this particular tree, you will insert 25. That means you will travel from the 70 to 14, 14 greater than 25 greater than 14, so go to the right. Smaller than 31, so go to the left. So greater than 23, you are going to insert here. So you notice that in your insert path, along this path, all the nodes, their balance factor are 0. All the nodes, the balance factor are 0. That means this particular path, along this particular path, each nodes are well balanced. Their left side and right sides are equal. So that means the height of the left subtree and right subtree of node 70, the left subtree, right subtree of node 14, the left subtree and right subtree of nodes 31, and also the 23 before insertion, they all are well balanced. They are equal height. The left subtree and right subtree are equal height. So their balance factor all are 0. So of course, if I insert a node there, it won't affect. It's still, yeah, every nodes, the difference still at most, the height of the left and right subtree of every node still different by at most 1. So there's no balancing issue. In short, I don't need to do anything. After insertion, everything look fine. Yeah, this one no problem. Another one, case 2 also fine. You insert 80. Trying to insert 80, that means it will be 80 is greater than 70. 80 is smaller than 93, so go to the left. 80 is greater than 73, so you'll go to the right. So you insert here. So in this case, you look at along. So after you insert, you start return. The balance factor is 0. The balance factor after you insert, originally is -1. After you insert it, you will become 0. Then this one also remains 0. So you'll find that after you return, this one will be from 0 become, after you insert this side, it will become -1. Then this one will become 0. Then this one, the left side, right side will be equal, so still remains 0. So again, by insert in, when you have a node along the path, yeah, you find that you are insert at the shorter subtree. Yeah. If it's -1, you insert at his left side. If it's 1, you insert at the right side. In that case, after you insert it, actually you're trying to make the tree better, more balanced. So in that case, again, there's no balancing issue. So these two cases are fine. The key is the next one. Yeah, you need to do the balancing is the next one. That's when you're trying to insert a node to the subtree, which is already higher than the other side. So that's when if you're trying to insert a node at the left subtree, but that left subtree is higher than the right subtree, you further insert a node will make it even higher. Then the whole tree will become unbalanced. That is the example. So the first case is I'm trying to insert the nodes at the left subtree as a left node, so called LL, left subtree of the left node. So this example is 95. I try to insert 95 into this. So 95 greater than 70, 95 greater than 93, 95 smaller than 99. So this 99 is already the left subtree is already higher because the balance factor is 1, indicate that the left subtree is higher. But you're still trying to insert the nodes at his left side. Then the 95 is smaller than 97. So you insert at its left side and as a left node. In this case, yeah, you will find that 99 along the path, 99 will be unbalanced. After insert the zoo, yeah, you need to, when you start return, you will update. So when you start return, you will update. After you insert successfully, you start return. When you return back to 93, you will update the balance factor. This balance factor now will become 1. Okay, 1 still balanced, so fine. But when you return to 99, this one, the left side, the height is 1. The right side, the height is -1. So the balance factor will become 2. So 99 will become unbalanced. Then we need to do something at 99. What we need to do, we will do the rotation. We will rotate right. In short, the idea to do the rotation is trying to move some nodes at the left subtree to the right so that you will balance. Now, that's what I mean locally balanced. You're only trying to reshuffle the nodes in this region. Yeah, among this part, you need to do the balancing. How to do it? So after I insert, yeah, the order something wrong. Yeah, after I insert the nodes, you will update. After I insert the nodes, you will update the height to 1. Then you update the height to the height of the left subtree is 0. The right subtree is -1. So the balance factor will be 1. The height of the 93 is 1. The balance factor also 1. Here is the balance factor. Here I only indicate the balance factor. I didn't indicate the height for you because I'm only interested about the balance factor. So the balance factor is 1. Then I trying to, this one okay, no problem. Then I go back further. Yeah, then I start update the height of the 99 because later you on top you need to do. So you need to update the height first. Then after you update the height, you check the left subtree. The left subtree height is 1. The right subtree is -1. 1 minus -1. So which is 2. Yeah, the thing goes wrong. Yeah, this one you need to balance. So indicate that the 99 is unbalanced. So this one is not balanced. You need to do something. So we need to do the rotate right about 99. How to do this? This thing, first, you have the nodes 99. Then you have a nodes 97. Then you have a nodes 95. Let's say here got something. If this is just an example, in case you have something here, So first step you need to do is let the nodes 97, which is the child of 99, the left child of 99, the 97 right child, left child, right child, the 99 left child, 90 right child, this part to form this 99 to be 99 left child, whatever here. What if anything here, you will become the left child of 99. And then, of course, because this, if there's something at the right child of 97, definitely those number definitely is smaller than 99. If you have anything here, yeah, this thing definitely smaller than 99. Smaller than 99, so I put under the left child of 99. And then let the nodes 99 be the right child of 97. So 97 will move up. And then let the 97, so 97 still carry 95 at the left side. Then 97 now become the parents nodes of 99 and 95. Then 97 will be returned to 93. So you can see that this is trying to move the 99 now, then move the 97 up. Yeah, you do the rotation. Rotate about, yeah, rotate right about 99. After you rotate it, this is after the rotation. This is after the rotation. So you will find that after you rotate it, this portion, the tree will be balanced, will become balanced. 95, the balance factor 0. 99, the balance factor is 0. 97, the balance factor is 0. 93, yeah, after that, you return all the subtree still balanced. This part is height is 1. This part, the height is 0. So 0 minus 1, you get minus 1, still remain minus 1. Yeah, 70 still remain balanced. So after do the rotation, the tree will be back to AVL tree, so-called a balanced tree. Okay, so this is you insert a node at a left subtree at its right child, at the left child. So LL case, I call it LL case. So what if 99 got the child? So it's still okay. If there's anything here, it will be here. If originally this one got something, then this one got any triangle. So the triangle will be here. The circle will be here. Yeah, this subtree will remain at the right subtree of 99 will still remain at the right subtree. The left subtree of 99 will carry the right subtree of 97. So you're trying to rotate the nodes to let the 97 become parent, then let the 99 become its left child, and become its right child, sorry. Become its right child. So he's trying to rotate. After do we need to update? Of course, you need every time after you need to update the height, because after you rotate, the height will be different. So you need to update. Yeah. So this is the algorithm. So I first trying to get, in this case, let's say my nodes is 99. So this is the current nodes. Then my X will be 97. The right child in this case is the null pointer, which is trying to point here. Yeah. Then this is X. This is XR. But this is a null pointer in this case. Then you will let the current left point to, yeah, so this one will point to here. Then X right will be update. X right will update to point to this. Yeah, this is what these two steps doing the rotation. After the rotation done, you need to update 99 and 97, because 99 and 97 the position change, so their height will change. So you need to update their height. You need to check their height. So it's like to get the height of the left subtree and right subtree, then plus 1. Either, yeah, see which one higher, then plus 1. And then you return x. So return x means that you will return x back to 93. 93 will update the subtree accordingly. So this is the right rotation. Okay, so and similar, just now is the left subtree insert as a left node. Similarly, there's the right subtree insert at the right node. So 12 is the example. Yeah, maybe I stop here. I think Monday I can carry on to talk about it. But in short, you expect that in this kind of things, summarize AVL3. Okay, first two case, that's when you insert the nodes at the balance path. The path, along the path, all the balance factor of the nodes are 0, then no problem. If you insert a nodes, the path, the insert nodes, the path is there's a -1 or 1, but you are trying to insert at the shorter subtree. Then that's when after your insertion, the whole tree look more balanced. Then in that case, there's no balancing issue. You have the balancing issue is only when you're trying to insert a node into the subtree, which is higher than the other subtree. In that case, you expect that the one of the nodes will become the height, the balance factor will become more than 1 or more than or less than -1. That means they are no longer at most 1. The difference may no longer at most 1. So it's probably will be 2 because you insert a nodes only. If you insert only a nodes, probably they will become 2 or -2. In that case, yeah, you'll be like this case will become -2. Earlier case, yeah, this node will become -2. The earlier case is become 2, either -2 or 2, because you only insert one node. So in that case, you probably need to do something on that particular node to balance it. Earlier one is rotate right, this one will rotate left. Yeah, these are 2 cases. Another 2 cases is trying to insert the left subtree right nodes and right subtree left nodes. That, because you insert here or here, you insert something here or here, or the earlier one, you're trying to insert 90 something, 95 or 98, you will make the tree unbalanced. So total, you expect that there are 4 cases. I will discuss, but these 4 cases, they are using the similar approach. Today, I only show you the left subtree, left nodes. You insert the new nodes into the left subtree, and the left subtree which is higher than the right subtree, and the left subtree and at its left node, left child. So in that case, you need to do the rotate right. You need to move some nodes from the left to the right to balance. In this case, you will move the nodes from the right to the left to balance it. So that is the balancing. I'll go through this again on Tuesday lecture. Yeah. So about the RR case and LR case and the RL case. So total there are 4 cases. Okay. How do we do the lab question? Which lab question you are referring? So that is the today lecture. Yeah. So in the Tuesday, we have covered the binary search and the time complexity, and then the nodes insertion and the nodes removal. So after you able to insert the nodes into the binary search tree, you will find that if you insert the nodes in the in certain scenario, like just now the example 3, 2, 1, you will end up that your binary search tree is unbalanced or is a linked list. So this is not something we want to have for a tree structure. If you want to have this kind of tree data structure, you will just simply use the linked list to construct a simple linear data structure. Since you are using a non-linear data structure, of course you wish that you form a tree structure. And from the time complexity analysis of the binary search, I have shown you to have a complete binary tree, you will improve your search time complexity from linear time to log n. Yeah. So therefore, we introduce you this AVL tree balancing to improve the tree structure. And this part again, don't try. It's not ask you to memorize the rotate left and rotate right. I will go through how to do the things, but it's let you to understand how when you face a problem, how people analyze it. Actually, they will find what are the case there's no balancing issue, what are the case there's a balancing issue, and then among the balancing case issue, they categorize into 4 cases, and then they try to solve each of them. Then they find that actually in the end they just need 2 functions, rotate left and rotate right. Yeah, so that is the topic we cover in this lecture. And I will release the binary search lab soon, by probably by tonight. Yeah, I will release it for next week. Yeah, next week we still have the 1 lab section and 1 tutorial. I will release the question probably by today or tomorrow. And I think tomorrow I will still go through this week lab section during the weekend. Later I will make the announcement. Probably will do it around 11 o'clock tomorrow to go through the lab. I will make the announcement to confirm the time. Probably 11, 11 or 12. Yeah. Okay, so if you have any question, yes. If not, that is okay. If you have any question, you can post your question here, or if not, you can drop me an email. Sorry about that, because one day I received the email is really scary. I may not reply your email. So in that case, you probably need to send me the email again, because there are too many email I received in a short period of time. Sometimes I may miss out. Yeah. So again, this particular AVL tree just give you the idea. Of course, you can see that insert a notes. Later you will find that if you want to remove a notes, the task is you need to do a lot more. Then not surprising that we won't ask you to implement this whole function during the test. But you need to understand how to rotate left and rotate right. That maybe sometimes you may use it. And also the thing you need to learn, I highlight here. Yeah, you should understand how to, when you face a problem, how actually people find there's a balancing problem. They not just simply use the sorting. Yeah, you know that the sorting is not efficient. You should try to think whether there's a way to improve the time complexity. And then you're trying to find out, actually among these, there are 4 cases, there are 8 cases, there are 10 cases, and then how they trying to categorize the problem into, group the cases into a few sub problem. And now they find that they just need to do the rotation left and rotation right, and then they solve the problem. And then at that point they start implement and solve the problem. Yeah, when you face a big problem, you are not just simply immediately write the code and use like kind of a brute force to try all the possible case and then solve it. Yes, sometimes you want to improve the efficiency, you really need to analyze all the cases and find out the common and uncommon part and solve it accordingly. That is something you need to learn. Yeah, the test, again, this is like why I just now need to mention this particular AVL tree is invented in 1962. So it's already for so many years ago. And then not surprising that you can go online and find out the code. So I don't like to ask this kind of question because I don't want you to memorize the code. This module is not ask you to memorize a code. It's give you a problem, whether you know how to solve it and whether how you realize and implement a program to solve the problem or not. That is the learning outcome. And not the learning outcome and go and memorize what is the AVL3 first step. Yeah, I need to do the balance or not balance, or I need to check the balance factor, or I need to got the case 1, R, L, or 4 cases. I need to memorize the step and code. That is not the learning objective of this module. Is you need to learn how people analyze the problem, not learn the answer, the solution. That's why I keep emphasize the lab or the is also not ask. Everyone keep asking me to give you the solution, but the objective is not learn the solution itself. It's learn how to get the solution, how to approach and analyze the problem and get the solution. And why the assignment so difficult? Also the same thing. The objective is let you analyze and find out the solution by your own. So I try not to make something you can easily find online. Yeah. So again, don't copy your friend's answer again. Yeah. Okay. If no further question, that is today's lecture. Thank you.